morning to everybody. My activity research is focused on the modeling and control of multi-phase synchronous motor for automotive application. So, the fault-tolerant capability of the multi-phase motor drive and the possibility to enhance the motor torque by injecting an higher order of stator current harmonics make the multi-phase synchronous motor suitable for electric and hybrid application. So, in the first part of this presentation, the modeling and control of the multi-phase synchronous motor in healthy condition is investigated. Then also the faulty condition will be covered, and finally the main advantage brought by the use of this type of motor in a hybrid electric vehicle will be studied. So, in order to make the model as general as possible, both the star and delta connected multi-phase synchronous motor are investigated, and the current and voltage terminal vector of a multi-phase machine are related to the phase ones by the connection matrix. Therefore, in a star connected phases, you can see that the terminal current flowing into the terminal is the same that flows into the phase. So the connection matrix is an identity one. While in a delta connected motor, using the Kirchhoff's law, the current flowing into the terminal is the difference between the current that flows onto two adjacent phases. So in this case, the connection matrix has this structure. Using this matrix as a fourth element connection block in the POG model, one can obtain a general model independent from the type of stator connection. In order to write the dynamic equation of the system in a more compact and suitable form, three different transformations have been proposed. The first one is real and the other two are complex. These transformations use a vectorial notation, and these transformations are power invariant. So this is the most important advantage with respect to the other transformation proposed in the literature. As shown in this figure, these transformations are equivalent from a mathematical point of view because it's possible to pass from one transform system to another one. Among these transformations, the best one seems to be this transformation because the transformed system has a reduced dimension. So in this slide, you can see the POG scheme of the motor. Note that the structure of the scheme is independent from the type of stator connection because only the connection matrix is modified from the star or delta connected phases. Between section 2 and 3, you can see the previous transformation that allows to write the dynamic equation of the system in a more compact form. And in this transformed system, you can see the electrical part of the motor, the mechanical part of the motor, and the connection block between the section 4 and 5 that allows to convert the power between the electrical domain to the mechanical one. Note that the dynamic equation of the system are complex, so also the real function must be used in the model. As I previously said, the most important feature of this transformation is that this transformation is power invariant, so the scalar product between the voltage and current vector that represent the power that flows through this section is equal to the real part of the complex power into this section. So the dynamic equation of the system in the complex rotating reference frame can be written in this vectorial form. This is a more general form that is independent from the number of phases of the motor. Note that the inductance and the resistance matrix in this transformed reference frame are diagonal. So the electrical equations are transformed, reduced, and decoupled. So each electrical equation is independent one from each other. This means that the multi-phase synchronous motor can be seen as a set of a fictitious machine. This concept is very important in the control, and it will be shown later. In this slide, you can see the simulating scheme of the system. This is the feedback, and this is the model of the multi-phase synchronous motor. Inside of this masked block, you can see this scheme. Note that there is a direct correspondence between this scheme with the POG scheme shown in the previous slide. So you can see the connection matrix, the transformation, the electrical part, the torque vector, and the mechanical part. The most important advantage of this model with respect to the other, it is that a unique general model has been obtained independent from the number of phases, the type of stator connection, the type of rotor flux. So this is a very general model. Note that thanks to this graphical user interface, a user can modify the number of phases, the type of stator connection, the electrical parameter, the mechanical one, and so on. Let me now move on to talk about the control of this type of motor. As I previously said, a multi-phase synchronous motor can be seen as a set of separated fictitious machines, so shown here. And the motor torque generated by the motor is equal to the real part of the scalar product between the transformed current vector to the torque one. So, in order to increase the quadrature component of the transformed current vector, it is necessary to feed the motor by injecting an higher order of stator harmonics. In the classical three-phase motor, only one harmonics is used to feed the motor. In a multi-phase synchronous motor, more harmonics are injecting, and each harmonic is related to a specific fictitious machine. The voltage and the current phases are bounded respectively by the maximum voltage Vmax and the maximum current Imax, so these two constraints must be satisfied in the control. And this constraint can be rewritten in the transform reference frame in these two ways. So in the control, it is necessary to decide how to distribute the maximum voltage V over line M and the maximum current I over line N into the component VMK and IMK. Considering the generic electrical equation of a fictitious machine, the voltage and the current constraint can be represented as a circle equation, and only in the intersection zone between these two circles can be used in the control. Distributing the voltage and the current constraint into the component VMK and IMK, you can modulate the amplitude of the radius of this circle. So this is the situation. Distributing the voltage V over line M and I over line M into the component of the subspaces, we modify the capability, the torque production capability of each subspace. This is a non-linear problem that can be solved considering the torque equation. I skip a lot of the mathematical detail. Anyway, three different torque control have been proposed. In the first one control, the current vector is parallel to the torque one. In this way, it's possible to minimize the dissipation of the system, and in this control, all the current and voltage constraints are distributed into all subspaces. And the second control maximizes the torque production of the multi-phase synchronous motor. So we decide to use the current vector which has the maximum projection on the torque one. In this control, the most of the current and the voltage constraint are applied only one fictitious machine. When these two previous control cannot be used, we propose a suboptimal control named the convex combination. So this is the simulation result of the multi-phase synchronous motor in healthy condition. The dynamic behavior of the motor velocity and the motor torque is shown here, and the corresponding trajectory on the torque plane is shown on the left figure. Note that the green zone refers to the minimum dissipation torque control. The white zone is forbidden because doesn't satisfy the current and voltage constraint. And the red one represents the zone where a convex combination is used. Note that between point B to point D, the motor torque is saturated in order to satisfy the constraint. Since we consider a 7-phase synchronous motor, we operate into three different subspaces shown here, and we feed the motor in injecting the first, then third, and the fifth components. So using the proposed control, the multi-phase synchronous motor is injecting the first three harmonics. Let me now move on to talk about the second topic of my research activity, that is the model and the control of the multi-phase synchronous motor in faulty condition. In this slide, you can see two different ways to simulate an open phase failure. In the left figure, a variable resistor is used as an open element, while in the right one, you can see that an additional voltage is used as an open phase element. So the left model is easier to implement as a physical meaning, because when the open phase faults occur, the phase resistance goes to infinite, so this is a physical meaning. But there is a simulation problem, because in simulation the smallest integration step is chosen as regard the smallest time constant. So when the resistance goes up to infinite, the pole of the system moves to the left, and this means that the time constant of the faulty phases decreases, and so it is necessary a very high simulation time. So to overcome this problem, we propose to use this second model in order to simulate the failure. This model has not a physical meaning. This is a trick, because an additional voltage is used to feed the faulty phases in order to obtain a zero steady-state current. In this way, the faulty phase resistance is not modified, and so one obtains the same simulation time with respect to the LT mode. Note that adding this voltage to this equation, one obtains this first-order system. So when the faults occurs, the current falls down to zero with this exponential law. In this equation, the unknown variable is the common voltage and the time derivative of the starting current. This unknown variable can be computed using proper transformation. And one obtains this POG model of the motor in faulty phase. Note that the mechanical part and the torque vector are unchanged with respect to the LT model, and only the electrical part is modified. This transformation is used in order to impose the star-connected constraint, and this is the dynamic equation of the electrical part of the system. An internal input, or OP, defines the time instant and the type of index of the faulty phases, and the function block phi compute the additional faulty voltage. In healthy condition, this faulty voltage is equal to 0, and in faulty condition, it has this structure. So the component of the faulty voltage related to the faulty phase are different from 0, and guarantees a zero steady-state current. So also this model can be directly implemented in Simulink, and it is independent of the number of faulty phases and the displacement of the faults. So this is the Simulink implementation of the model. Also, in this case, the model is masked, and this is the graphical user interface. Note that here the user can insert the time instant of the faults and the number of the faulty phases. Inside of this block, you can see the electrical part of the system. Also, in this case, there is a direct correspondence between the Simulink scheme with the POG1. This is the simulation obtained for a 5-phase synchronous motor when two non-adjacent open phase failure occurs. Note that the first faults occur on the second phases at a time at 8 seconds, and the current falls down to 0. And when also the second faults occur on the fourth phases, also its current goes down to 0. So in this case, we have only 3 current to generate torque in the motor. In this second simulation, 2 adjacent open phase failure is simulated. Also in this case, when the faults occur, the current goes down to 0. And in this slide, you can see the dynamic behavior of the multi-phase synchronous motor in faulty condition when the control is not modified with respect to the healthy condition. Note that when the faults occur, the mean value of the torque decreases and the torque ripple appears. This torque ripple is due to the magnetic interaction between the unbalanced magnetic field of the stator current and the symmetrical magnetic field generated by the permanent magnet. The worst case is when 2 adjacent open phase failure occurs. Note that in this case we have a very high ripple. So in this simulation, you can see that the motor can continue to work also in faulty condition, even if the control is not modified. But in order to obtain also in fault condition the desired torque without ripple, it is necessary to modify the control, and so it is necessary to take into account the faulty constraint. Note that the standard basic vector of the matrix TB select from the current one the faulty component and put it equal to 0. This constraint can be rewritten in the transformer rotating reference frame in this way, and the column of this metric represents the forbidden subspace, shown here as a black arrow. So this subspace cannot be used to control the motor. Its orthogonal complement is this plane represented here, represent the subspace that can be used to control the motor in faulty condition in order to obtain also in this condition the desired torque without ripple. So the torque vector must be projected onto the subspace of the remaining healthy current along the forbidden one, using this projection matrix. So, and using this torque vector into the minimum dissipation torque control, one obtain the reference current that provides the desired torque also in fault condition without ripple. The forbidden subspace is time variant, so also the torque vector is dependent on the electric angle of the motor, and it is describe a periodic trajectory on the subspace, so it's quite complex to control this system. Anyway, using a sliding mode technique, it's possible to implement the motor drive, and so using this control, the amplitude of the remaining healthy current increases, so it is necessary to take into account also the current constraint. From this constraint, one can obtain the maximum torque that satisfies the current limit, and so it is necessary to saturate the desired torque this maximum value in order to satisfy the current limit, because the theoretical maximum number of faults that can be occur in a multi-phase synchronous motor is ms minus 3. But in applying the proposed control, the current increases, so it is necessary to saturate their value. And you can see the simulation obtained for two adjacent open phases. Note that when the faults occur and the control is not modified, the torque mean value decreases at torque ripple ampere, so the motor decelerates. But when the fault-tolerant control is applied, the torque goes up to the desired value without ripple. As I previously said, this control increases the amplitude of the remaining LT current. So when in this second case, the current limit is not satisfied. So this simulation is repeated, taking into account also the current saturation. So note that in this case the current limit is satisfied, but saturating the torque provided by the motor, one obtain obtain a reduced performance of respect to the system. Note that the torque in this case is time variant, and in this second case one obtain a constant torque with a lower mean value. So this is the drawback of the system, but it is not a problem of the control. It is a problem of respect to the maximum current that the power device can be stand. So this is the final work of my research activity. This is the Toyota hybrid system. This system is implemented, for example, in the Toyota Prius. And here we have the classical three-phase motor replaced by two five-phase synchronous motor. The key element of this power traction system is the planetary gear. Note that the transmission and all motors are rigidly connected to the planetary gear, particularly the transmission and the electrical motor MG2 is rigidly connected to the ring. The engine is rigidly connected to the carrier, this one. And the last subsystem, that is the electric motor MG1, is connected to the sun. So these two electrical motor refers to the POG scheme of the the model of multi-phase synchronous motor in faulty condition, and the other subsystem have been implemented using the power-oriented graph modeling technique. So you can see the planetary gear, the engine, and the vehicle. All the model has been implemented in MATLAB Simulink, obtaining this whole powertrain model. You can see here the engine, the first electrical motor, the planetary gear, the second electrical motor, and the model of the vehicle. These two models has been shown in the previous slide. This green block refers to fault-tolerant control, and this orange block is the global control of the vehicle. An external urban driving circle has been simulated, and we decided to and the faults occur at this time instant on the motor MG2. Note that in this time the vehicle cruises at velocity 50 kilometers per hour, and the faulty motor is the only motor that provides the traction power. This is the condition. When the faults occur, the current falls down to zero, and the ripple appear on the torques related to the planetary gear. But the dynamic of the vehicle should be unaffected with respect to the faults because the motor can continue to work with the remaining 40 phases. This ripple can cause some mechanical failure, so it is necessary to modify the control. When the fault-tolerant control proposed during my research activity is applied, the torque ripple disappears, so the motor can continue to work safely. So in this presentation, general model of multi-phase synchronous motor in healthy and faulty condition has been proposed. In healthy condition, the multi-harmonic injection, considering also the voltage and current constraint has been investigated, and the minimum dissipation torque control has been extended also in fault condition. Finally, the advantage brought by the use of the multi-phase synchronous motor have been studied considering the specific hybrid electric vehicle. So this work is the starting point for future study on the use of this type of motor, for example, in electric vehicle. Unfortunately, I have only simulation results have been obtained, so it is a test bench should be implemented in order to obtain also some experimental results. These are my publications, so that's all. Thank you for your attention.
Any questions? A couple of questions. So first of all, you didn't find a company. Thank you. You didn't find a company which can provide a test bed. So
no, because the problem is that this type of motor are custom motor, and they cannot be found now in the market. So there is very high cost to buy one of this type of motor. And
how much could it cost?
I don't know, but
a few thousand
one order of higher respect the cost of classical three-phase motor.
Okay, and the second point is, so what about the novelty of the work?
Okay. First of all, is that this model are general possible, and the model doesn't depend with respect to the number of phases. In the literature, only model have been implemented considering a specific number of phases, a specific type of rotor flux. Instead, this model is as general possible, allows to simulate both one single failure, two adjacent failure, and so on. And this approach, we have implemented a library, so other architecture can be simulated, so this is in simulation. This is very important to understand the dynamic behavior, and using this model you can.
So general modeling, that's the first important contribution.
Yes.
And the second point about cost control techniques?
Yes, about the control of this type of motor in faulty condition.
Okay.
Because also this control is general and extend the minimum dissipation torque control in faulty condition. So also in faulty condition, one can obtain the desired torque without a ripple.
Okay.
Here you can modify the control, so there is a ripple and the mean value of the torque decreases. When the fault-tolerant control is applied, a torque ripple without motor torque without a ripple can be obtained.
Okay, and maybe in the car companies in this area,
yes,
there are not hybrid vehicles, so that's the problem, which is a pity because all this could be tested in a realistic scenario. Okay, thank you very much again. The next one is Mr. Luca Ferrari. Okay, thank you.